Okay, determine the pH as the equivalence point for the titration of the 200 milliliters of the sodium cyanide. So the concentration is 0.0525 more. And you're going to use 0.0375 more of the HCl to do the titration. So first, we can write down the reaction equation. That is, you have the HCl will react with the sodium cyanide to produce sodium chloride and HCN here. So the reaction is 1-to-1 ratio. So from here, the first thing, right, we can calculate is the moles of the sodium cyanide in this reaction. So the moles of the sodium cyanide equals to the concentration times volume. The concentration is given 0.0525. And the volume here is 200 milliliters. So it's 200 over 1,000 liters. And that's equal to about 0.0105 more. So in this case, since the reaction ratio is 1-to-1, and we want to calculate the pH at equivalence point. So that means at equivalence point, the moles of the HCl that is added into the solution should be equals to the moles of the sodium cyanide. So that's equal to about also 0.0105 more. So in this case, we can calculate the volume of the HCl that is added into the initial solution. So it's moles of the HCl over the concentration of the HCl. So it's 0.0105 over, in this case, the concentration is 0.0375. So that's about 0.28 liter. So it's about 280 milliliters. So from here, the first thing we can calculate is after the titration, the total volume of the solution. So that's equal to the initial volume of the cyanide plus the volume of the HCl that is added. So that's 500 plus 280. So that's 780 milliliter. And also, in this case, we find since it's stoichiometric reaction, all the sodium cyanide and the HCl will be converted into the HCN. So in this case, the moles of the HCN will be equal to the moles of the HCl or moles of the sodium cyanide. So that's about 0.0105 more. So in this case, we can calculate after the titration, right, the concentration of the HCN equals to the moles of the HCN over the volume of the HCN. So that's 0.0105 over here it's 780 over 1,000 because we use liter as unit. So now the concentration becomes 0.013 3.46. So now, right, all the protons comes from the HCN. So now we can treat the problem to what is the what is the pH of this HCN solution? So that means the HCN would dissociate into protons and CN minors. From here, we can make an ice table. So initially, you have this 0.01346 moles of the HCN. You don't have any protons and CN minors. And let's assume X more was consumed. So we produce X more proton and X moles of the anions. So in the end, you have 0.01346 minus X, X, and X. So the Ka of this reaction can be expressed as the concentration of the proton times the concentration of the cation ions and over the concentration of the HCN. So that's equal to X squared over 0.01346 minus X. And that's equal to the equilibrium constant is given here. So it's 4.9 times 10 to minus 10. And if we do some approximation, it becomes X squared over 0.01346 equals to 4.9 times 10 to minus 10. So let's do the calculations. So the X will actually becomes 1.91 times 10 to minus 4. So in this case, right, this is the concentration of the protons. So then the pH would be minus log the X. And that's equal to 3.72. And that is the answer. That's it.